Hello there, and welcome to the Sleepless Scientist, a quiet little corner of the cosmos where your thoughts can slow down and curiosity drifts into something calm and luminous. Tonight, we'll explore one of the most hauntingly beautiful questions science has ever asked, one that lives at the crossroads of physics, philosophy, and wonder. Why is our universe so perfectly tuned for life to exist at all? Before we set off, if you enjoy these soft journeys through space and thought, I'd be truly grateful if you'd take a moment to like this video and subscribe. Only if these calm explorations bring you a bit of peace. And when you can, leave a comment to tell me where you're listening from and what time it is there. It's always incredible to see how many corners of the world gather here together in this quiet hour. Now, dim the lights, let the hum of your room become part of the background, and settle in. If your mind begins to wander, that's perfectly okay. Just let it drift. We'll still be here, unfolding the story softly, one thought at a time. Imagine looking at the universe not as an ocean of chaos, but as a delicately woven fabric. A tapestry whose every thread, each particle, each force, each constant is stitched with such remarkable precision that if pulled even slightly out of place, the whole pattern would unravel. Stars wouldn't form, planets wouldn't orbit, chemistry wouldn't happen, and life, as we know it, or perhaps in any form at all, would never arise. It's easy to forget how much balance lies beneath the surface of our ordinary lives. You might glance out your window and see a tree swaying in the breeze, or the faint golden line of sunlight slipping over rooftops. But behind that peaceful picture is a universe that behaves just so. A universe where gravity has exactly the right strength to hold planets in gentle orbit, but not so strong that everything collapses in on itself. A universe where the atom holds together without being too clingy or too loose. Where stars burn slowly and evenly, giving off light for billions of years instead of exploding or fizzling out too fast. You could think of it like baking, if baking required your ingredients to be measured not just in teaspoons, but to the 120th decimal place. A little too much salt, and the cake's too savoury. A little too much gravity, and the cake becomes a neutron star, not a great snack. Scientists call this phenomenon the fine-tuning of the universe. It's the idea that many aspects of the cosmos, its physical laws, its starting conditions, its fundamental numbers, appear to be set within incredibly narrow ranges. Ranges that, if they were even slightly different, would not allow life, complexity, or structure to exist. Now, some people see this and wonder, how can that be a coincidence? Surely there must be a reason. Others argue that it's not surprising at all, because only in such a universe would anyone be around to notice. And still others take a more imaginative route, asking, what if our universe is just one of many? Or even more curiously, what if it's not real at all? These questions don't have simple answers. In fact, they may not have answers at all. At least not in the way we're used to thinking. But they offer something even more valuable in a sleepy moment like this. They give us a place to wonder. They invite us to lie back, breathe slowly, and imagine that we are part of something vast, strange, and delicately improbable. Because we are. You, listening to this, are made of atoms that once drifted in stellar clouds, born from stars that burned long ago. Your body, your thoughts, your heartbeat, all depend on forces and particles that behave with a consistency so reliable, we rarely stop to appreciate how fragile it all is. You don't need to understand quantum mechanics or memorize constants to sense the miracle of that balance. You're living it, moment by moment, breath by breath. So tonight, let's float gently through the ideas. We'll talk about distances and stars, about atoms and gravity, about constants and coincidences. We'll visit different explanations that scientists and philosophers have offered, some grounded in data, others perched on the edge of imagination. But always with calm, with awe, with the kind of quiet you feel when you look up at the night sky and realize you're standing on a speck, floating in a gentle sea of stars in a universe that doesn't crash or collapse, but instead quietly allows you to exist. You don't need to choose a side tonight. You don't need to believe or disbelieve, to explain or defend. You're allowed to simply wonder, to rest inside the question. That's the gift of these quiet hours. So if you're ready, let's begin where all good stories do, with the setting, the place, the soft cradle of conditions that make Earth a home, and the universe, a place where life can bloom. Let's explore just how perfectly this world seems to be arranged, and whether perfection is ever really perfect at all. If you've ever sat by a window on a quiet afternoon, watching the sun drift across the sky, you've witnessed something far more miraculous than it first appears. The sun rises, it warms your skin, it paints shadows across your living room floor. It seems ordinary, familiar, but what it represents is nothing short of astonishing. An alignment so precise that it allows oceans to remain liquid, leaves to unfurl in spring, and breath to rise gently from a sleeping body. Our Earth sits in a very narrow zone of space around the sun. Not too close, not too far. Just the right distance for water to flow, clouds to form, and life to flourish. Astronomers call this the habitable zone, but you might know it better by a more playful name, the Goldilocks zone. Not too hot, not too cold, just right. If Earth were nudged just a little closer to the sun, about 5% closer really, the oceans might begin to boil and the atmosphere could become a thick, choking soup like Venus. Push it 5% farther away and we'd begin to freeze like Mars locked in a deep, silent chill. But we're not too close, and we're not too far. We orbit the sun in a gentle ellipse that keeps us within a life-permitting temperature range all year round. This isn't something we had a hand in. It's a gift, a cosmic coincidence, or perhaps something more, depending on how you see it. And the sun itself isn't just any star. It's stable, long-burning and remarkably quiet compared to more volatile stars that spit out intense radiation, or burn through their fuel too quickly to support planets for long. Our sun is a bit like a calm parent, holding a steady warmth over us, never rushing, never erupting wildly, at least not often. It's easy to forget that this giant ball of plasma 93 million miles away is the reason you're alive. But even the perfect distance and a patient star wouldn't be enough without another companion in the sky. The moon, glowing softly in the night, does more than decorate the darkness. It stabilizes the Earth's axial tilt, the angle at which we spin relative to our orbit around the sun. That tilt is what gives us seasons. Without the moon's gravitational tug, the Earth might wobble unpredictably over long stretches of time. That wobble would make climates chaotic, swing temperatures wildly, and destabilize the delicate rhythms on which ecosystems depend. But instead, we have gentle springs and long, leafy autumns, predictable enough to plant crops and build civilizations. The moon keeps its face turned toward us as it orbits, always the same serene expression. It's easy to think of it as a passive observer, but really it's a quiet partner, holding the Earth's balance like a steadying hand on a child's shoulder. And then there's Jupiter, the guardian of the outer solar system. Massive, swirling and distant, it doesn't seem like it should matter much to us here on Earth. But Jupiter's gravity is so strong that it acts as a kind of cosmic broom, sweeping up comets and asteroids that might otherwise come hurtling inward. It's taken many hits for us over the history of the solar system. Without Jupiter, Earth might be bombarded far more frequently by space debris, events that could easily reset the clock on life or wipe it out entirely. So while Jupiter spins far from our skies, its role is anything but remote. It's the big sibling on the playground, intercepting flying objects before they reach the more fragile younger ones. Even the location of our solar system within the Milky Way contributes to the calm that life needs to grow. We live in a relatively quiet suburban spiral arm of the galaxy, not too close to the dense, volatile core, where radiation storms and black holes are more common. Here, in this quieter lane, stars are spaced far enough apart that they don't often disturb one another's planets, and cosmic events don't regularly bathe everything in destructive energy. Imagine living in a neighbourhood where the storms don't reach, where the houses don't shake, and the lights stay on reliably. That's our little cosmic cul-de-sac. Of course, none of this means Earth is perfectly safe. We've had impacts, we've had extinctions. The universe still rolls its dice from time to time. But on the grand scale of things, on the scale of what might have been, we live in a pocket of rare gentleness. And that's worth noticing. The more we learn about planets around other stars, the more we realise how precarious this setup really is. Many exoplanets orbit their stars too closely, tidally locked so that one side burns in eternal daylight, while the other freezes in endless night. Others have wildly elliptical orbits, extreme atmospheres, or no moons at all. Some may still be habitable, of course, in ways we don't yet understand. But it's becoming clear that Earth is not the default. It's a peculiar success story in a universe filled with near misses, and yet, despite all these narrow margins, here we are, breathing, thinking, listening. It's easy to fall into the habit of seeing the world as mundane. The sidewalks, the clouds, the way your cat settles into a warm patch of sunlight. But behind that ordinariness is a cosmic choreography that had to unfold with stunning precision. A dance of distance, gravity, and time that allows you to sip tea, read a book, or lie quietly and listen to a voice drifting through your headphones. Perhaps it's chance, perhaps it's necessity, perhaps it's something else. But whatever the reason, the result is this. A little blue planet in a quiet corner of a vast, ancient galaxy, wrapped in just the right conditions for life. And tonight, as you rest in that life, maybe you'll feel a little closer to the moon, a little more grateful for the sun, and a little safer knowing that Jupiter is still up there, quietly watching the sky. If someone handed you a recipe card yellowed at the corners and soft from use, with only 6 ingredients written in careful handwriting, you might not expect much. 6 items, no instructions, no measurements, just the essentials. And yet, those 6 ingredients might be all that's needed to bake a universe. Not just any universe, but one in which atoms can hold hands, stars can burn gently, and life, eventually, might find its voice. This idea comes from the British cosmologist Martin Rees, who identified 6 numbers, just 6, that seem to underpin everything we see in the cosmos. They are not just abstract symbols tucked inside equations, they are the deep parameters of reality. If even one of them had been slightly different, the universe might have been stillborn, lifeless, silent, or so chaotic that no structure could ever form. Let's drift through them now, one at a time, like stepping stones across a dark pond. We won't get lost in the mathematics. There's no need. What matters is the sense of balance, the improbable harmony humming beneath everything we know. The first number is n. It represents the strength of gravity compared to the strength of electromagnetism. It's a huge number, about 10 to the 36th power. That means gravity is, on average, 10 followed by 36 zeros times weaker than electromagnetism. And that's a good thing. If gravity were just a little stronger, say only 10 to the 34th power, we might live in a universe where everything collapsed too quickly, where stars burned too fast and exploded before they had time to form planets. But if gravity were even weaker, matter might never clump together at all. No stars, no galaxies, just an even mist of particles forever drifting apart. The number seems odd, arbitrary even, but it isn't. It's essential. The second number is epsilon. This one governs how firmly atomic nuclei stick together. It's the reason why fusion happens inside stars and not in your coffee mug. If this number were just a touch smaller, the universe would be made of only hydrogen, too large, and stars might never form at all because everything would fuse too quickly. But at its current value, 0.007, fusion works just right. Stars burn steadily. Elements form. Life can build its complex chemistry atop this quiet burning. The third number is omega. It tells us the total amount of matter in the universe. Is it enough to pull everything back inward into a big crunch, or too little, letting the universe expand forever into icy silence? As it turns out, the actual value is right at the razor's edge, astonishingly close to the critical value needed to produce a flat, balanced universe. Any more and space would have curled inward, any less and it would have expanded too quickly for galaxies to form. Instead, we live in a Goldilocks cosmos. Again, not too much, not too little. Then there's lambda, the cosmological constant. This one might be the most shocking of all. It represents the energy density of empty space, what we call dark energy. This force is pushing the universe apart, accelerating its expansion. But it's doing so very gently. If lambda were larger, the universe would have expanded too fast for galaxies and stars to coalesce. If it was smaller, or negative, everything might have crumpled inward long ago. The value of lambda appears to be fine-tuned to a staggering degree. Some estimates say to 1 part in 10 to the power of 120. That's a precision that makes engineers weep and philosophers blink. It's like setting your thermostat to a temperature so exact that deviating by a single atom's width would either freeze or incinerate the house. The fifth number is Q. It measures the lumpiness of the early universe, how uneven the cosmic microwave background was after the Big Bang. If Q were too small, gravity wouldn't have enough unevenness to pull matter together into stars and galaxies. Too large, and the universe would be dominated by massive black holes and violent collapse. Our Q sits just right, about 1 part in 100,000. Just enough structure to get things started, just enough silence to let them grow. And finally, there's D, the number of spatial dimensions. It might seem obvious that space has 3 dimensions, left, right, forward, back, up, down. But what if it didn't? With only 2 dimensions, gravity wouldn't work the way it does. Stable orbits wouldn't be possible. With 4 or more, forces would weaken too quickly over distance, or atoms might not be stable. 3 dimensions may not be the only possibility in theory, but it appears to be the only one that allows a stable, complex, and long-lived universe. Put these 6 numbers together, and you get something that, on its surface, seems miraculous. Not because they follow some divine symmetry, not because they spell out a secret message, but because they don't have to be what they are. They could have been different, and in almost every other combination, they would have been catastrophic. Think of them like the settings on a cosmic control panel. If even one dial had been turned a hair too far to the left or right, nothing we recognize, no planets, no chemistry, no thought, would have emerged. And yet, here they are. Balanced, hidden, unquestioning. Like the strings of a violin tuned in a cold room, never snapping, never slipping out of key. This doesn't necessarily prove anything. It doesn't tell us why these numbers are what they are. But it invites wonder. It stirs the soft suspicion that perhaps, behind the math, behind the quiet ticking of natural law, there is a deeper pattern, or at least an exquisite accident. Sometimes the most ordinary things, light through a window, the pull of the ground beneath your feet, are only ordinary because of cosmic choices made billions of years ago in conditions no one can fully explain. And sometimes it's enough just to notice, to breathe in a universe that has allowed itself to be understandable, at least a little. To lie still under stars that burn with a fusion shaped by epsilon, held together by n, cooled just enough by q, and whispered into shape by lambda. The numbers don't shout, they don't argue, They simply are. Some things in life feel comfortingly stable. The slow swing of a grandfather clock, the hum of the refrigerator in the next room, the way sunlight finds its way through the same window each morning. They are small anchors in a world that is always shifting, but even those quiet patterns rest upon something deeper, something older and far more unchanging. Beneath every tick of time, beneath every glimmer of light or ripple of warmth, lie the constants of nature, invisible, silent, unwavering. They do not ask for attention, yet without them, the world would fall apart before it ever began. Let's rest for a moment in that stillness. The universe, for all its motion and noise, is built upon a few rules that have never, as far as we can tell, been broken. These rules aren't enforced by any agency or mind. They are not printed in ink or etched into stone, but they exist everywhere and always in the same exact way. The strength of gravity, the charge of an electron, the speed of a light in a vacuum. These values are fixed across time and space. Whether you're here on Earth or drifting between galaxies, whether you're measuring a falling apple or watching the light curve around a black hole, these constants remain as steady as the stars. Let's begin with gravity, the most familiar and the most mysterious of them all. It's the force that tethers you to the ground, that guides planets in their orbits, that shapes galaxies into spirals and clusters. You might think of it as gentle, because it feels that way in daily life. A slow fall, a soft pull. But in cosmic terms, gravity is immensely influential. What makes it remarkable is not just that it exists, but how weak it is compared to the other forces. In fact, it's astonishingly weak, so much so that it takes an entire planet to hold a person down. The gravitational constant, denoted by G, is one of the smallest numbers in physics, but it's exactly as small as it needs to be. Make gravity just a bit stronger, and stars would burn too fast and too hot, exhausting their fuel before life had a chance to emerge. Make it weaker, and they might never ignite at all. G sits in a sweet spot that lets stars simmer gently for billions of years, long enough to cook up complexity. Then there's the electromagnetic force, responsible for the way atoms hold together and for nearly every chemical reaction that makes life possible. Its strength is defined by a constant known as alpha, or the fine structure constant. It determines how strongly electrons are held in orbit around atomic nuclei. If alpha were slightly larger, electrons would cling too tightly to their atoms, and complex chemistry would be stifled. If it were smaller, electrons might drift away too easily, leaving atoms too unstable to build anything meaningful. But at its present value, around 1/137th, this balance allows atoms to interact, to bond, to share energy. It's the quiet handshake of the universe, repeated endlessly in every cell, every star, every breath. Next, we arrive at the proton to neutron mass ratio, a number that might seem obscure but is crucial to the stability of matter. Protons and neutrons are the building blocks of atomic nuclei. Their masses are very close, but not identical. If the proton were just slightly heavier than the neutron, hydrogen, the most abundant element in the universe might not exist. If the neutron were significantly lighter, it might never decay, and the balance of elements formed after the Big Bang would be radically different. This small asymmetry shapes the entire periodic table from the helium in balloons to the iron in your blood. Another indispensable value is the strength of the strong nuclear force, the force that binds protons and neutrons together inside the nucleus. Without it, atoms would disintegrate. If it were slightly weaker, atomic nuclei wouldn't hold together. If it were slightly stronger, the universe would be flooded with heavy elements, and the delicate balance needed for life might never emerge. It's a force that works only over extremely short distances, far smaller than an atom. But its effects are felt in every stable element, in every burst of energy from a star. Together, these constants form a kind of scaffolding beneath the cosmos. They don't evolve, they don't adapt. They are not pushed around by temperature or time or choice. They simply are. And this is where things become quietly astonishing. We have never observed these constants to change, not once, in all the experiments we've conducted, across all the light years we've measured. The light from distant galaxies, millions or even billions of years old, bears the same spectral signatures we see in labs on Earth. The chemistry of a far-off star is the same chemistry that brews a cup of tea in your kitchen. That sameness across time and space is what makes science possible. It's why we can build models, make predictions, design telescopes, and decode starlight. The universe speaks a single language, and it's the same language whether whispered through quantum fields or shouted in supernovae. The constants are the grammar of that language, and somehow, without prompting, without rehearsal, they harmonize. It's tempting to call this balance perfect, but perhaps that word is too heavy, too final. The universe is not perfect in the sense of being flawless. After all, it's full of violence, supernovae that tear apart stars, black holes that devour light, gamma-ray bursts that sterilize entire solar systems. But even so, within this great unfolding, there exists a kind of coherence, a trustworthiness. The constants of nature don't change their minds. They hold the same tune no matter how loud the symphony becomes, and maybe that's what makes them beautiful. We tend to think of beauty as something visible, sunsets, frost patterns, the curve of a shell, but there is beauty too in what never wavers, in what remains still while everything else moves. Like the center of a turning wheel, these constants are the quiet heart of physics. You may never see them directly. You may never write them down or hold them in your hand, but they're always there, beneath your feet, in your breath, inside every star you've ever wished upon. And tonight, as you lie still in your own quiet orbit, perhaps there's comfort in knowing that somewhere far away, a galaxy is spinning exactly as it should. Not because anyone told it to, not because it's being watched, but because the constants never blink. They simply keep being what they are. Before there were stars or atoms or even the familiar concept of space and time, there was something. Not a place, not a thing, not even a darkness, just potential. A poised stillness teetering on the edge of unfolding. Then, in a moment so brief it could barely be called a moment, the universe began, not with a crack or a pop or a theatrical explosion, but with a stretch. The Big Bang, despite its name, wasn't like dynamite or thunder. It was more like the sudden, silent unfurling of an immense fabric. Space itself expanded not into anything but into being. Time began ticking, though there was no clock. Energy flooded out, though there was no source. This was the beginning of everything we know, not a flash of light in darkness, but the birth of light and darkness alike. In those first fractions of a second, the universe underwent something called cosmic inflation. It didn't just grow, it ballooned, faster than the speed of light, which sounds impossible until you remember that light moves within space, while inflation was an expansion of space. Distances that were smaller than atoms suddenly became vast. This rapid expansion smoothed out any initial wrinkles, like a bedsheet stretched across a mattress in one impossibly perfect pull. But here's the delicate part. The rate of that expansion had to be exquisitely precise. If the universe had expanded just a little more quickly, matter would have thinned out too fast. There wouldn't have been enough time or density for atoms to form, for gravity to gather clumps of matter into stars. On the other hand, if expansion had been just a tiny bit slower, everything might have collapsed back into itself, like dough too heavy to rise. Instead, the expansion rate balanced on a razor's edge, quick enough to prevent recollapse, but slow enough to allow complexity to eventually bloom. In the background of all this was another kind of drama, one not of speed, but of symmetry. In the earliest phase, all the fundamental forces of nature, gravity, electromagnetism, the strong and weak nuclear forces, were unified. They were not separate things, but different expressions of a single underlying force. But as the universe expanded and cooled, this symmetry broke. It was like a pristine snowflake beginning to melt, revealing hidden patterns as it dripped into something less uniform but more interesting. This process, known as symmetry breaking, gave rise to the distinct forces we know today. Gravity split away first, like a shy dancer stepping quietly to the side. The strong nuclear force peeled off next, followed by the weak nuclear and electromagnetic forces. Each separation was a kind of cosmic choice, a branching path in the unfolding script of the universe. And each choice narrowed the range of possibilities, shaping how matter could behave, how energy could move, how the universe could build its future. It's difficult to overstate how delicate these transitions were. The energy levels involved were colossal, far beyond anything we can replicate in laboratories, but the outcomes were subtle. A slightly different trajectory in this breaking of symmetry could have led to a universe with no gravity at all, or a gravity too strong to permit stars, or no matter, just light and emptiness, forever ricocheting off itself. Instead, the unfolding was just so, as though the universe wasn't exploding randomly, but performing a slow, deliberate exhale. In this early phase, there were no atoms yet, just a dense soup of quarks, gluons and leptons, particles that danced wildly, colliding, transforming, vanishing and reappearing. It was chaotic, yes, but it was not disorderly. Even this apparent frenzy followed rules laid down by the very constants we met earlier. The constants held steady even then, allowing a kind of order to whisper through the storm. As the first full second approached, the universe was already cooling. The high-energy collision slowed, and the soup began to settle. Quarks grouped into protons and neutrons. Photons, the particles of light, began to lose some of their dominance. And time, which had only just begun, was already shaping a story not of randomness but of possibility. This is the strange beauty of the early universe. In its most primal form, it wasn't shaped by structures or stars, but by balances. It wasn't yet beautiful in the way a nebula is beautiful, with colours and light and dust. But it was beautiful in its restraint, in the way every unfolding was allowed, but not forced, in the way everything that could happen didn't happen, only what was just right. Think of it like the first few seconds of a symphony. Before the melodies intertwine, before the strings swell, there's a pause, a moment where silence leans forward, a breath of possibility. The Big Bang was that breath, but one where the air exhaled became space, time, and energy itself. Even now, 13.8 billion years later, we can detect whispers of those first seconds, not in echoes we hear with our ears, but in the way galaxies are arranged, in the way light bends, in the way the sky itself glows faintly in microwave radiation. The memory of that first expansion, that first symmetry breaking, is still written across the cosmos like a signature beneath a painting. And so, the universe, once compact beyond comprehension, became a vast and stretching plain, not chaotic, not wild, but poised, a place where laws could begin to operate, where matter could begin to gather, where one day a warm little planet might orbit quietly around a yellow star and wonder how it all began. That beginning was not violent, not angry, not loud. It was simply precise. There's something deeply comforting about the idea of cooling down. A cup of tea left on the windowsill slowly losing its steam. The sun sinking behind the trees, drawing colours across the sky that weren't there an hour ago. The hush that follows excitement. We often associate heat with energy, action, urgency, and cold with quiet, with things finding their shape. In the early universe, after that first astonishing moment of expansion and unfolding, things were hot, inconceivably so. Particles flew in every direction, colliding with unimaginable energy, transforming from one state to another in a blur of creation. But eventually the universe did what so many things in nature do. It began to cool. Not quickly, not dramatically, but steadily. And in that cooling, order began to take hold. Roughly 3 minutes after the beginning, still well within the first breath of cosmic time, something beautiful happened. The universe reached a temperature and density that allowed the first true atomic nuclei to form. This stage is known as primordial nucleosynthesis, and it gave us the lightest elements, mostly hydrogen, and a smaller amount of helium, along with traces of lithium. This may sound simple, but it was far from guaranteed. For these elements to form, the conditions had to be balanced just right. If the universe had expanded more rapidly, it would have cooled too quickly for nuclei to stick together. If it had expanded more slowly, the intense heat and density would have torn nuclei apart before they could stabilize. But in the version of the universe we inhabit, the expansion rate was once again delicately tuned, allowing the process to run for just long enough to yield the ingredients that would someday ignite in stars. Think of it like baking. There's a certain moment when the heat is enough to rise the dough, but not so intense as to burn it. The universe, in its earliest oven, baked a recipe of hydrogen and helium in exactly those proportions. About 75% hydrogen, 25% helium. And then the heat dropped. The oven door closed, the fusion paused, and the universe went quiet again. But that hydrogen and helium weren't the end of the story. They were the beginning of a new kind of potential. These were the raw materials that billions of years later would collapse into stars. Fiery furnaces where the heavier elements would be forged. Without the initial balance of nucleosynthesis, those later stars would never have had the right kind of fuel. Iron, carbon, oxygen, the materials that make up planets and people, would have remained forever out of reach. And yet, the early universe didn't leap straight into stars and galaxies. There was still a long, long way to go. After nuclear synthesis, the universe was still a hot, dense plasma, an ocean of charged particles and light, tangled up so tightly that photons couldn't move freely. It was bright, but not in the way we think of brightness. It was a brightness trapped inside a fog, a soft candle smothered beneath a thick blanket of heat. Then, around 380,000 years after the Big Bang, an immense span compared to those first few minutes, but still a blink in cosmic terms, the fog began to clear. Electrons finally paired with nuclei to form neutral atoms, and when that happened, light was no longer trapped. Photons could move freely for the first time. The universe became transparent. That ancient light is still travelling today. It's known as the cosmic microwave background, or CMB for short, and it's one of the most important clues we have about those early moments. Like a photograph taken in the soft morning of existence, the CMB is an image of the universe when it was just a baby, only 380,000 years old, its surface still smooth and warm. But the most fascinating part of this image isn't how bright it is, it's how slightly imperfect it is. Across the CMB, if you could see it as a map, you'd notice tiny temperature fluctuations, just one part in 100,000. These minute irregularities are not flaws, they're the fingerprints of creation, tiny pockets where the density was slightly higher or lower. Those pockets would, under gravity's influence, grow over billions of years into the galaxies, clusters and superclusters we see today. Without those gentle imperfections, the universe might have remained a formless cloud of gas. No stars, no planets, no life. Just a smooth, dark emptiness. But with them, with just the right amount of unevenness, matter began to gather, to swirl, to ignite. It's strange to think that everything we know, from the swirl of galaxies to the warmth of your breath, was once seeded by tiny ripples in a glowing fog. But perhaps that's how most things begin, not with declarations or designs, but with small, quiet differences. a hint of structure where none was expected, a bump in the silence that becomes a melody. So as the universe cooled, it didn't fade away. It prepared, it laid the groundwork, it handed off the baton from temperature to structure, from noise to form, and all of it, every stage, had to follow a delicate sequence. Too much fluctuation, and the universe would fragment into chaos. Too little, and it would stay a smooth soup forever. Instead, the balance was perfect enough to allow imperfection to flourish, and in that, all things began. Perhaps that's the deeper meaning behind cooling. Not loss of energy, but the birth of shape. A soft landing after the wildness of beginnings. A time to settle, to pause, to allow new rules to take hold. And as you lie here tonight, breathing in the quiet, it might comfort you to know that the atoms in your body were once part of that fog. That same light, the ancient CMB, is still whispering around you, faint but constant, a lullaby from a time before stars, a reminder that even the hottest beginnings can lead to the calmest forms. Now the fog has lifted, the light is free, the universe is no longer a formless fire, no longer the roaring soup of particles slamming against one another in infinite heat. It is cooling, stretching, quieting, becoming transparent, like a pond settling after a rainstorm. And in that clarity, gravity begins to sing its long, slow song. What had once been the tiniest ripples, minute temperature variations in the cosmic microwave background, are now the seeds from which structure will grow. Some regions, a little denser than others, tug on the matter nearby. That tug becomes a pull, the pull becomes a fall, and the fall becomes the beginning of shape. Matter does not merely gather, it folds, swirls, clumps and spirals. And so, the grand architecture of the cosmos begins to rise. In these dense patches, hydrogen and helium drift toward one another, pulled by gravity's quiet insistence. The gas clouds contract, compress, and warm. As pressure builds in their hearts, something miraculous happens. The temperature rises to millions of degrees, and fusion begins. Tiny atoms, light as whispers, are pressed together until they become something new. Helium from hydrogen, then heavier elements from helium. In this way, the first stars are born. These first stars are not like the sun you know. They are enormous, short-lived and brilliant, burning with an intensity that would make our own star seem like a candle beside a furnace. They live fast, die young, and in dying explode in cataclysms so vast they outshine entire galaxies. These explosions scatter the heavier elements they created, carbon, oxygen, iron, into the surrounding space, enriching the gas clouds around them. The universe is no longer just hydrogen and helium. It is becoming more interesting, more complex, more alive with potential. As time goes on, these enriched gas clouds give birth to new stars. But this time the stars are different. Smaller, longer-lived and surrounded by disks of matter. In these disks, dust grains bump into one another, stick, clump, and form the seeds of planets. Gravity, again, is the architect, pulling, shaping, organizing, and slowly galaxies take form. Not just stars, not just clusters of gas, but great spiraling cities of light. Some are shaped like elegant pinwheels, others like luminous clouds, others like vast globes of fireflies drifting through night. Each one contains billions, sometimes trillions of stars, all born from the same primordial materials, all pulled into structure by gravity, all orbiting a quiet center where stars are densely packed, and time seems to slow. Galaxies do not exist in isolation. Like dancers on a great floor, they move in patterns, pulled by the gravitational cords that stretch between them. Some drift past one another without touching. Others collide, slowly, gracefully, over hundreds of millions of years. Their stars rarely crash directly, but their shapes twist, Spiral arms stretch like fabric caught in wind, and eventually they merge into new forms. Larger galaxies, different rhythms, and sometimes central black holes that grow vast and dark and endlessly hungry. And through all of this, the same rules hold. The same constants we spoke of earlier, the strength of gravity, the mass of protons and neutrons, the ratio of forces, all remain unchanged. They are the invisible stage beneath this cosmic choreography, the music that guides the dancers. Without them, no galaxies. Without galaxies, no stars. Without stars, no planets. Without planets, well, we wouldn't be here, wondering about any of this. It's worth pausing to consider how unlikely it all is. If the density of matter in the early universe had been slightly different, just a smidge higher or lower, none of this might have occurred. If the clumps in the cosmic microwave background had been too small, gravity would not have had enough to work with. The universe would have remained smooth, dull, and uneventful. If they'd been too large, the universe might have collapsed into an unruly mess of black holes and radiation. But instead, they were just right. Enough lumpiness to create structure, not so much to destroy it. Enough chaos to birth beauty, not so much to end it. Even the shape of space matters here. Observations tell us that the universe is geometrically flat, meaning parallel lines will stay parallel forever. This flatness is critical. It allows for the even spread of matter and the smooth growth of galaxies. A curved universe would behave very differently. But again, we find ourselves in that rare balance, where the fabric of space-time is stretched just so, not too tight, not too loose. And so, the universe, still young but growing older by the millions of years, becomes a place of pattern, a place of gravity's fingerprints, where galaxies orbit one another in great clusters, forming filaments that stretch across the cosmos like delicate threads in an invisible web. Between these filaments lie great voids, empty regions where matter never clumped, vast gulfs of darkness where light barely passes. It's easy to think of this structure as grand and cold, but it is also, in its own way, intimate. Every atom in your body, every calcium speck in your bones, every carbon link in your cells was forged inside a star formed from a cloud shaped by a galaxy seeded by a ripple in the early light of the universe, which means that your very presence here is part of that ancient dance. You're not outside it, looking in. You're a note in the melody. So as you rest tonight, picture the galaxies turning, slowly, majestically, like dancers who have always known the steps, no rush, no error, just movement guided by invisible hands and quiet rules. The galaxies do not ask why they exist. They simply move, shine, and continue. And perhaps that's enough, for them and for us. Somewhere in a quiet corner of one of those galaxies, orbiting a rather unassuming yellow star, a planet formed. It was not too hot, not too cold. It had liquid water, a stable climate, and a calm place in space to grow old in. But even that wasn't enough. The planet could have been beautiful, even comfortable, and still remained empty forever, unless something very strange and very rare began to happen within its oceans, its rocks, its heat, and its storms. The birth of life requires more than the right temperature or the right distance from a star. It requires chemistry, very specific chemistry, and the more we study it, the more we realize just how unlikely that chemistry really is. At the heart of all living things is carbon, a quiet, unassuming element that sits modestly in the middle of the periodic table. It's not the most abundant, it doesn't glow or react violently, and yet it is the only known element that can form long, stable, complex chains of atoms. Carbon can bond with itself, with hydrogen, oxygen, nitrogen, and more, building rings, branches, double helixes, and twisting spirals. It's the scaffolding of life, the gentle architect of cells, proteins, DNA, and everything that pulses or breathes or thinks. If carbon couldn't do what it does, if it were a little more reactive or a little less flexible, then molecules couldn't grow beyond simple shapes. Life would be stuck at the level of chemical soup. No complexity, no self-replication, no adaptation. Just drifting molecules, forever searching for a shape they can't quite hold. Water, too, plays a role so subtle and yet so essential that it's easy to overlook. It is a universal solvent, capable of dissolving more substances than any other liquid. This means it can carry nutrients, distribute heat, and act as the perfect medium for biochemical reactions. But water is also unusual in other ways. It has a high specific heat, which helps stabilize temperatures. It expands when it freezes, making ice float instead of sink, allowing lakes to freeze from the top down, protecting life beneath. And its molecules stick together just enough to allow surface tension, droplets, and clouds. No other liquid behaves quite like it. No other liquid is so forgiving to the fragile dance of a life. Then there's oxygen, the quiet oxidizer. Too much of it, and the world would burn in a flash. Too little, and life would suffocate before it began. But in the right balance, oxygen fuels metabolism, allowing energy to be unlocked in controlled, gentle steps. It binds to hemoglobin in your blood. It reacts in your cells. It is, in many ways, the breath of transformation. But it is only one player in a symphony of precise, interwoven properties. And this is where things begin to feel improbable, almost absurd in their specificity. For life to arise and then evolve into the dizzying variety we see today, a cascade of physical and chemical coincidences had to line up. The strength of chemical bonds had to fall within a narrow range, not too weak to fall apart, not too strong to resist change. The spacing of electrons around atoms had to allow for predictable interactions. The energy levels of molecules had to permit complex reactions without collapsing into chaos. Every step in the ladder of life is built on a rung of chemistry that didn't have to exist. Imagine trying to build something as delicate as a spider web, not from silk, but from warm butter and wet twine. That's what life would be trying to do if the chemistry of our universe were just a little off. And yet, here we are. Not only possible, but inevitable. Not only fragile, but persistent. Even the periodic table itself, the arrangement of the elements, reflects a deeper order. The gaps between the elements, their properties, their behaviours, all stem from quantum mechanics and electromagnetic forces working together in precise harmony. The fact that carbon can bond with 4 other atoms, that water can form hydrogen bonds, that metals can carry charges, none of these were guaranteed. They are consequences of deeper truths, of physical constants that seem to have been written with life in mind. Some scientists have pointed out that if the resonance levels of carbon nuclei were different by just a few percent, stars could not create enough carbon through fusion. This is known as the Hoyle state, a specific energy level predicted by physicist Fred Hoyle that turned out to be exactly where it needed to be for stars to produce abundant carbon. Hoyle himself, a committed atheist, found the precision unsettling. He once remarked that it seemed as if a super intellect has monkeyed with physics. He didn't mean it literally, but the sentiment echoes what many feel when faced with such delicate balances. And yet, all of this, the chemistry, the constants, the cascading improbabilities, doesn't necessarily imply intent. It might still be the result of natural laws playing out over time, with randomness, trial and error on a cosmic scale. But whether accidental or not, it's hard to escape the feeling that we live in a universe that, against all odds, has made room for breath, for thought, for wonder. You might be tempted to ask, was this all necessary? Did it have to be this way? Could there have been other forms of life based on silicon or ammonia in universes with different rules? Perhaps, perhaps not. But what we do know is this. In our universe, with our rules, carbon chemistry is the only known way to build something as elaborate and self-aware as you. Every heartbeat, every memory, every dream relies on a chemical choreography that seems almost too precise to believe. And yet, it's happening, right now, without fanfare, without fail. So tonight, as your body settles into rest, remember this. You're not made of random atoms thrown together by chance. You're made of patterns, chemical, physical, cosmic, that go back to the first stars, the first elements, the first quiet cooling of a young universe. You're built from carbon's patience, from water's grace, from oxygen's fire, and perhaps most beautifully, from a universe that said yes, when it so easily could have said nothing at all. Imagine walking into a room and finding a chair perfectly shaped to hold you. The back curves just right for your spine, the legs match your height exactly. The seat is neither too hard nor too soft. You might ask, who made this for me? But then again, you might consider, perhaps you noticed the chair only because it already suited you. Maybe you ignored the others, the ones too tall or too narrow, because they were never going to be your chair to begin with. This is the soft logic behind something called the anthropic principle, an idea so quiet, so self-contained, that it almost feels like a tautology. It doesn't seek to explain the fine-tuned nature of the universe so much as acknowledge that our ability to notice it is part of the answer. We're here, wondering, because we live in a universe where it's possible to wonder, and that single fact limits the kind of universe we could ever find ourselves in. There are two main versions of the anthropic principle, the weak and the strong. The weak anthropic principle states simply that the physical laws and constants of the universe must be compatible with the conscious life that observes them. In other words, it is not surprising that we see a life-permitting universe, because if the universe had not permitted life, there would be no one here to see it. It's a little like marvelling at how dry it is inside your house, while it rains outside. Of course it's dry. You're indoors. The conditions required for you to observe your comfort are already part of what makes that comfort possible. So perhaps we shouldn't be surprised to find ourselves in a universe where planets form, water flows, chemistry builds complexity, and minds can reflect, because only that kind of universe allows for observers in the first place. The strong anthropic principle goes a step further. It suggests that the universe must have those life-permitting qualities, not just by coincidence, but as a kind of necessity. It implies that the universe is in some sense required to produce observers like us, that life is not an accident, but an expected result. This view tiptoes toward purpose, though not necessarily divine purpose. It suggests a universe that bends in some quiet way toward consciousness. But whether one accepts the weak or the strong version, the core idea remains the same. We are not separate from the universe's conditions. We are their product. The observer and the observed are not on opposite sides of a window. They are reflections of the same glass. Some critics say the anthropic principle isn't really an explanation. They call it circular. They say it answers, why is the universe the way it is? With, because we're here. And maybe that's true. But maybe there's still something quietly profound in that circularity. A gentle reminder that the very act of asking is already shaped by the answer. Imagine again the universe as a vast, dark forest. Countless clearings, countless paths. Paths some are barren, some are wild and inhospitable, but one clearing contains the conditions that allow a campfire to be lit. And by that fire sits a figure, wondering aloud, why this clearing? The answer, perhaps, is simple. This is the only place the fire could burn. It doesn't mean the clearing was made for the fire, but once the fire exists, it can only do so in a clearing just like this. The anthropic principle doesn't try to peek behind the curtain of reality. It doesn't ask whether the constants were chosen or accidental. It simply observes that given all the ways a universe could be, most of them wouldn't allow life to even begin. And yet, somehow, here we are, noticing, questioning, dreaming. There's something comforting in this if you let it be. It means that your existence is not an error. You're not a statistical fluke or a mistake. You're part of the universe that permits noticing, a thread in the fabric that includes its own awareness, a ripple in the sea that can reflect on the sea itself. Maybe in the quiet hours, this is the kind of answer that matters most. Not because it solves the puzzle, but because it changes how we look at the pieces. We are not watching the universe from the outside. We are the part of the universe that looks back at itself. Even the word anthropic, from the Greek anthropos meaning human, doesn't have to mean human-centered. It can mean mind-centered, consciousness-centered, the capacity for awareness, for perspective, for awe. Whether we are the only mind in the cosmos or just one flickering candle among many, our ability to ask why is itself a rare and precious outcome of billions of years of quiet unfolding. So tonight, as you lie beneath a ceiling or a sky, know that your being here is not trivial, not accidental. You're part of the only kind of universe that could ever include you, not because the stars conspired to make you, but because you are what happens when hydrogen waits long enough. And in that simple truth, there's a kind of magic, not loud or showy, but soft and steady, like the whisper of the anthropic principle itself. Let's say you're walking along a beach and you find a single seashell, spiraled just right, coloured like ivory tea, unbroken despite the wind and waves. It feels too perfect to be an accident. But then, you glance up and realise the shore stretches endlessly in both directions. Thousands, maybe millions of shells lie scattered in the sand. Suddenly, the one in your hand doesn't seem miraculous. It's special because you picked it up. But it's not the only one. This is the quiet invitation of the multiverse idea, not to diminish the beauty of our universe, but to suggest that its perfection might not be unique. It might just be one of many. In the past few decades, physicists and cosmologists have begun to consider that our universe, with all its finely tuned constants and delicately balanced forces, may not be all there is. Instead, it could be just one bubble in a vast, frothing sea of universes, a single ripple in a grander ocean. The idea sounds fantastical at first, like something borrowed from science fiction, but it arises naturally from serious attempts to explain the strangeness of our own reality. If the values of the fundamental constants seem improbably well suited for life, perhaps it's not because they were chosen for us, but because all possible values exist, each in its own separate universe, and we happen to find ourselves in the one where life is possible. One version of this idea comes from inflationary cosmology, especially the work of physicist Alan Guth. In the inflationary model, the universe underwent a period of exponential expansion just after the Big Bang, growing from subatomic scales to astronomical ones in a fraction of a second. But some theories suggest this inflation never truly stopped. Instead, it continued in different regions, creating an endless series of bubble universes, each with its own set of physical laws and constants. You can picture this like a pot of boiling water. Each bubble that forms is a new universe. Some collapse right away, some grow large, some are lifeless, with laws that make chemistry impossible. Some flicker with potential, and in one of those bubbles, this one, everything came together just right. Another multiverse model emerges from quantum mechanics, the strange theory that governs the tiniest parts of reality. In one interpretation, every possible outcome of a quantum event actually occurs, each in its own branching timeline. The universe splits, not just once, but constantly, creating an unfathomable number of parallel realities. In some, stars never form. In others, they shine but never give rise to life. In a rare few, the conditions align so precisely that life not only emerges, but begins to ask questions. A third approach comes from string theory, a framework that attempts to unify all the fundamental forces into a single theory. String theory allows for a vast landscape of possible universes, each defined by different configurations of extra dimensions and fundamental constants. There may be 10 to the 100th power, or more different ways these variables could be arranged, each leading to a different kind of universe. Most are probably sterile, but a few, just a few, might look like ours. The beauty of the multiverse idea is not that it makes our universe less meaningful, it's that it allows for meaning without requiring a miracle. If enough universes exist, each with different parameters, then it becomes statistically likely that some will be life-permitting, and of those, a few might even allow conscious observers to evolve and reflect on their origins. It's not that our universe was chosen, it's that we, like the person who picked up the seashell, found ourselves in one that fits. This perspective doesn't demand belief in an infinite number of worlds. It doesn't insist on fairy tales. But it does offer a quiet resolution to the question of fine-tuning. If the dice were rolled only once and they came up exactly right, it might seem unbelievable. But if the dice are rolled billions upon billions of times across countless realities, then even the rarest outcome eventually appears. And in that universe, ours, life can begin to wonder. Of course, we cannot yet observe these other universes. They may lie forever beyond our reach, separated by barriers of space, time, or fundamental difference. But their existence is not pure fantasy. They are suggested by the math, the physics, the logic of models that otherwise make successful predictions. Like shadows cast by unseen figures, they hint at something more. Still, we must move through this idea gently. The multiverse does not eliminate mystery, it simply changes its shape. Instead of asking, why is our universe so perfect? We ask, why does the multiverse exist at all? Why does it produce so many possibilities? The question of origin remains, but it moves deeper into softer ground. And perhaps, most profoundly, the multiverse teaches us something about our place in the story. If we are one conscious ripple among countless unconscious waves, then our presence still matters. Not because it was destined, but because it happened. Against every odd, it happened. Tonight, if you close your eyes and imagine yourself as a small bubble on the surface of an infinite ocean, you are not diminished. You are not lost. You are the bubble that notices it is a bubble. You are the part of the ocean that reflects, and somewhere, out there, or perhaps not out there at all but folded into the idea itself, other bubbles rise and fall, some warm, some cold, some silent. But in one, this one, a question formed. A voice asked why, and that is something truly rare. We often imagine the universe as a place filled with things, stars, planets, atoms, light. But underneath all of that, beneath the forms and forces, is a quiet, elegant structure, mathematics. Numbers that do not fade, ratios that do not wobble, patterns that repeat with uncanny consistency across space and time. Even when the universe is loud and chaotic, the math remains silent and exact, like a scaffolding no storm can bend. Some thinkers have wondered, what if this mathematics isn't just a tool we use to describe the universe? What if it is the universe? This is the provocative idea behind physicist Max Tegmark's mathematical universe hypothesis. It's a strange thought at first glance, and yet it carries a curious simplicity. If the universe is mathematical at its core, if every particle and every law is just an expression of abstract relationships, then the reason for its specific features might be that they are the only logically consistent ones. In other words, maybe the universe couldn't be any other way. Instead of asking why does gravity have this value, or why can carbon bond the way it does, perhaps we should ask, what kinds of mathematical systems allow for stable structures at all? If the set of such systems is small, then maybe the universe we live in is not unlikely. It's inevitable. This is not the same as saying the universe was designed to be this way. Rather, it proposes that the rules we observe, those finely tuned constants and equations, are simply the only ones that don't fall apart. Like trying to build a bridge, only certain arrangements of supports and tension will hold. All the rest collapse. We are living in the solution that works. Imagine trying to draw a triangle. You quickly realise there's only one way to do it with 3 straight lines. They must connect at 3 points. Any attempt to bend the rules, adding a 4th side, curving one of the lines, creates something else entirely. A triangle is what emerges when the rules of Euclidean geometry are followed to their natural end. It isn't chosen, it simply is once the conditions are met. Now imagine that our entire universe is like that triangle. Perhaps space, time, and the laws of physics are what happen when certain abstract truths intersect. The speed of light, the strength of gravity, the structure of atoms. Maybe these are the necessary results of a deeper logic, not optional, not adjustable, just the only consistent answer to a set of cosmic equations. This idea has both a comforting clarity and a strange sort of austerity. It tells us that the universe is not an accident, nor a miracle, but a structure, like a crystal that forms when the temperature is right, or a melody that arises naturally from the keys of a piano. It doesn't need a composer. The notes are already there. The math plays itself. But then again, there's something oddly beautiful about that. Because if the universe is mathematical, then every part of it is connected, not just by forces or particles, but by principles. The same equations that describe the curve of a distant galaxy also describe the arc of water pouring from a faucet. The same logic that governs the fusion in the heart of a star governs the way your neurons fire when you remember a loved one's smile. You're not separate from this system. You're a pattern within it. There's a kind of elegance in seeing yourself this way, not as an exception to the rules, but as their inevitable outcome. Not as a disruption in the order, but as the order itself, walking and breathing and wondering. And if all of this seems abstract, you're not alone. The idea that the universe is math and that we are math too can feel cold at first. Numbers don't love, equations don't dream. But maybe that's not quite true. Maybe love and dreaming are what certain mathematical patterns do when they get complicated enough. When they loop back on themselves, when they remember, when they anticipate. Maybe consciousness is what math looks like when it becomes aware of itself. It's not the kind of explanation that offers comfort in the traditional sense. There's no guiding hand, no grand design in the way we usually imagine it. But there is a kind of peace in knowing that the universe is coherent, that it follows rules not because it must obey, but because those rules are the only ones that hold. That you, sitting quietly in your room, are not an outsider looking in, but a ripple in the system, a note in the chord, a solution in the equation. And if the universe is a mathematical structure, then perhaps every experience, every breath, every thought, every dream is a part of that structure unfolding itself, one moment at a time, not chosen, not random, but inevitable. So as you drift into sleep tonight, think of yourself not as a body resting in a bed, but as a constellation of relations, a dance of probabilities, a quiet harmony of forces, a brief and beautiful solution in the great math of the cosmos. You're not here by mistake. You're here because this is what can be. And somewhere, in the stillness of numbers too vast to name, the equation continues. Let's take a gentle step away from particles and equations and walk quietly into an idea that's more modern myth than settled theory. One part philosophy, one part computer science, one part science fiction. It's the suggestion that this universe, this vast and ancient space with its galaxies and gravity and finely tuned constants, might not be physical in the way we imagine. Instead, it might be running, like a program, a simulation. At first glance, it seems absurd, but stay with the thought. Let it unfold slowly, like a dream you're not sure is yours. This line of thinking was brought into sharp focus by philosopher Nick Bostrom, who proposed a trilemma, a kind of logical triangle with 3 points, one of which, he argued, must be true. First, perhaps civilizations like ours never reach a level of technological sophistication capable of simulating entire universes. Maybe they destroy themselves or lose interest. Second, maybe they do reach that point but choose never to run such simulations. And third, if they do have the technology and the interest, and if they run many such simulations, then the number of simulated universes would vastly outnumber the single real one. In that case, the odds that we are living in the original, physical universe would be very small. In other words, if simulations are possible and common, then statistically we're probably in one. It's a strange thought, and yet, the more we look at the structure of our universe, the more it starts to resemble a kind of code. Space, for example, is not infinitely smooth. At the smallest scales we can currently theorize, space seems to be quantized, made up of tiny indivisible units called Planck lengths. You cannot measure anything smaller. That's not a matter of limitation, but of definition. It's like trying to slice a pixel in half. You can't. It's already the smallest possible bit of resolution. Time, too, may be granular, not continuous like water, but ticked forward by some fundamental beat. Energy levels are quantized, information seems to be limited. The laws of physics appear in some ways to be rules applied locally and consistently, like the logic of a program running across a vast network. There are even proposals in theoretical physics that suggest the universe may store and process information much like a computer. Quantum mechanics, for all its weirdness, is a probabilistic system that collapses into defined states only when measured, as though certain parts of the world only render when observed. Just like in a video game, where the distant trees are not drawn until the player turns their gaze toward the horizon. Of course, these are poetic comparisons. No physicist claims that we live in the Matrix, with wires in our brains or artificial pods beneath the surface of reality. The simulation hypothesis isn't about an evil overlord creating illusions. It's about the idea that what we call physical reality might be substrate independent, that it could in principle be emulated by a complex computational system. But then you might ask, if we are inside a simulation, who or what is running it? That part naturally is speculation. It could be an advanced civilization from a universe like ours, or a completely different form of intelligence. Or perhaps there is no runner at all, just a self-sustaining mathematical structure that executes itself, like a fractal, endlessly recursive with no outside needed. This view raises curious implications about fine-tuning. If we are in a simulation, the constants of the universe might have been set not by chance, nor by necessity, but by design. Not design in the theological sense, but in the engineering sense. A simulation must be stable. It must run within certain parameters. It must permit interesting complexity, especially if the goal is to simulate life, evolution, or consciousness. From that perspective, fine-tuning is not surprising. It's required. And if the simulation is being run many times, with slightly different settings, then again, we arrive at a kind of multiverse, but one made of servers and sequences, not space and time. Still, we should be careful. The simulation hypothesis, like many philosophical ideas, cannot currently be tested. We have no way to examine the edges of the universe and find programming errors or lines of code. Some researchers have proposed looking for unusual constraints in physical constants or unexplained computational limits, but so far no such evidence has surfaced. If we are in a simulation, it is a very good one, and yet there is something poetic in the idea, because even if the universe is not running on silicon and circuits, it might still be following rules that are in essence programmatic, executed rather than written, played out rather than guided. And if that's the case, if you are the result of an unimaginably complex process unfolding according to precise rules, does it make your existence less meaningful or more? Imagine being a character in a novel. You do not control the ink or the pages, but within those constraints, you live, you feel, you change, you fall in love, make choices, and carry memories that feel real, because they are. The framework may be artificial, but the experience is not. So if this is a simulation, it is one that includes beauty, it includes music and heartbreak and the taste of strawberries. It includes quiet nights like this one, where the only thing pressing against your mind is the slow drift of thoughts that have no destination. Maybe, in the end, it doesn't matter whether the universe is real in the way we once thought. What matters is that it is consistent, that it allows for moments of reflection, that it creates space for consciousness to arise and wonder. And tonight, as you rest, think of this not as a game to be solved, but as a dream to be lived. Whether simulation or structure or something stranger still, the world you touch is the only one you've ever known. It has held you this far. Let it hold you a little longer. There's a certain comfort in old questions, not because they're solved, but because they've been asked for so long. The idea that the universe might have been made, not just by laws or chance, but by intention, has whispered through human thought for thousands of years. Long before telescopes, before quantum fields, before theories of inflation or multiverses, people looked at the stars, the seasons, the spiraling patterns of shells and storms, and wondered if perhaps there was a mind behind it all. This isn't a new idea, it's an ancient one. And while it has taken many forms, gods, spirits, creators, watchmakers, it always circles around the same quiet intuition that something this intricate, this harmonious, this improbably suited for life might not be random at all. In philosophy, this thought often traces back to Aristotle, who proposed the existence of an unmoved mover, something that set everything into motion but was itself untouched by time or change. In his view, every effect must have a cause, and if you follow that chain of causes back far enough, you eventually arrive at something that simply is, something eternal. Not a god in robes, but a principle, a still point in a turning world. Later, thinkers like Thomas Aquinas expanded on this idea. He spoke of contingency, that most things in the universe could have been otherwise. They don't explain themselves. A tree grows from a seed, which comes from another tree which was pollinated by bees, which evolved in ecosystems, which depend on the sun, which formed in a galaxy, and so on. Each thing is dependent on other things. But if everything is contingent, you end up with a chain that needs an anchor, a necessary being, a foundation. Then came the scientific revolution, and with it, a new metaphor, the clockwork universe. Sir Isaac Newton imagined the cosmos as a grand mechanical system, predictable, orderly, running on the laws of motion and gravitation. And behind that system he saw a designer, the clockmaker, a being who did not need to wind the machine constantly, but who had crafted its precision so perfectly that it could run on its own. In more recent times, the idea of a designer has evolved, not always as a religious belief, but as a philosophical curiosity. The notion of intelligent design suggests that certain features of the universe and of life are best explained not by chance or natural processes, but by purpose. That complexity, especially the kind that involves information, organization, and adaptability, might point to an underlying intelligence. This argument often draws on examples from biology. The structure of DNA with its code-like patterns, the interlocking systems in cells, the way ecosystems function with such delicate interdependence. For some, these are signs of design, not emergence. Not random assembly, but crafted function. Still, mainstream science maintains that evolution by natural selection offers a powerful explanation for the complexity we see in living systems without invoking a designer. Over time, through countless tiny changes and selective pressures, simple organisms can give rise to astonishing complexity. The appearance of design, they argue, is not proof of intent. It is the outcome of survival, shaped by environment and mutation. But even outside of biology, the idea of cosmic design persists. In the fine-tuning of the universe, the constants that must align so precisely for stars to form, for chemistry to function, for life to exist at all, some find a hint of authorship. Not proof, just suggestion. As if the universe is not only functional, but beautiful in a way that feels chosen. And yet this path must be walked gently, because the idea of a designer, while comforting to some, can feel limiting to others. It risks ending the conversation with, "It was meant to be," when perhaps the more helpful approach is to keep asking, what are the patterns? What else might we discover? The point here isn't to prove or disprove, it's to reflect, to notice that this question still lingers, even after all our theories. That it persists not because we lack knowledge, but because we are moved by wonder. So if you imagine the universe as a work of art, it might be tempting to ask about the artist. If you see a pattern that stretches across galaxies and into your own heartbeat, it's natural to wonder if someone, or something, meant for that to be. But maybe design doesn't always require a designer. Maybe pattern is a feature of reality itself. Or maybe, just maybe, there is a mind behind the laws, not watching, not judging, but dreaming. A quiet presence, like the rhythm beneath a lullaby, unheard but always felt. And if not a being, then perhaps an idea, an intention folded into the fabric of space and time, a purpose that isn't imposed from above, but rises from within. Not a master builder, but a whisper of coherence that moves through the dark and the light alike. Whatever the truth may be, it's okay not to know, to rest in the question, to hold the possibility that the universe is more than mechanics, more than math. That maybe, just maybe, it's also a story. And tonight, as your thoughts soften and drift, let that story wrap around you, not as dogma, but as possibility. A gentle invitation to wonder, because whether crafted or emergent, chosen or chanced, this universe holds you, carefully, curiously, as if you were always meant to be here. Picture a meadow in spring, soft light, new shoots rising from the earth, insects tracing lazy circles in the air. It feels like it was made with care, deliberate, beautiful, even designed. But no gardener planted each flower. No hand arranged the wings on each bee. What you're seeing is the result of something quieter, slower and deeper. Evolution. Nature's long memory. Her patient way of solving problems by simply trying, over and over again, and letting what works continue. When people hear the phrase fine-tuning, they often think of it as something that needs intention behind it, like tuning a piano or adjusting a telescope. But biological fine-tuning doesn't work like that. It doesn't begin with a plan. It begins with variation and ends with survival. It's not about foresight, it's about feedback. A process that repeats so many times that complexity emerges naturally, not because someone built it, but because it's what was left standing. In the simplest terms, evolution by natural selection works like this. Random changes, mutations, occur in the genetic code. Most are neutral, some are harmful, but a few are helpful. These helpful changes give organisms a slightly better chance of surviving, reproducing, and passing on their genes. Over countless generations, these small advantages add up. Like drops of rain carving stone, they shape life. This is how wings emerged, not all at once, but step by step. From flaps that helped creatures glide, to more efficient motion, to true flight. It's how the eye formed, not from nothing, but from light-sensitive cells, which became curved surfaces, which eventually focused images. Every piece had a purpose, even before the full picture was complete. No master blueprint was needed, just the pressure to survive and the time to respond. In this way, evolution creates the illusion of design, not because it's random, but because it is relentlessly selective. Like a river shaping a canyon, it doesn't care where it's going, but it always finds a path. Now, compare this to cosmic fine-tuning, the precise values of gravity, electromagnetism, and particle masses that had to be just right for matter, chemistry, and stars to exist at all. That kind of fine-tuning doesn't iterate, it doesn't adapt, it just is. The constants of physics don't change across generations, they don't evolve. They are the background against which evolution can play out. And that's the distinction we must hold gently in our minds. Cosmic fine-tuning may be a prerequisite for life, but it doesn't tell life what to do next. Evolution is the sculptor. Fine-tuning is the studio in which the sculptor works. Still, it's tempting to look at something like the human brain, or even a humble ant, and say, surely this couldn't have come from randomness, and it didn't. Evolution is not random in its results. The mutations may be random, but the selection is not. It is ruthlessly consistent. Anything that increases survival gets passed on. Anything that doesn't disappears. What remains looks intentional because it works, because it's been tested, because it has earned its place through silent, invisible battles fought over millennia. So when we say, life finds a way, what we really mean is this. The universe provided a landscape rich enough, stable enough, and permissive enough for natural selection to take hold. And from there, life explored every corner of possibility. Not all life, not all at once, but slowly, tirelessly, without anyone watching. One of the most elegant examples of this is convergent evolution, the phenomenon where unrelated species develop similar traits because they face similar challenges. Eyes have evolved multiple times, independently, so have wings, so have tools, cooperation, even memory. Nature keeps arriving at the same solutions, not because it remembers, but because certain paths are simply more efficient, more stable, more likely to survive. The design isn't in the mind of a maker, it's in the logic of survival, and yet this doesn't mean the universe is indifferent, not entirely. For evolution to happen at all, the universe must offer a few critical things: time, space, variation, and stability. A star that burns too quickly won't give planets a chance to cool. A universe that collapses too fast leaves no room for complexity. The cosmos didn't have to be this friendly to adaptation, but it is. So perhaps the beauty of life lies not in its being designed, but in its being possible. That something as complex as photosynthesis or migration or memory can arise without a blueprint, but with enough time, enough pressure, enough chance, is not a lesser miracle. It is a quieter one, and we, with our cultures, our technologies, our questions, are just one thread in that long tapestry. We are what atoms do when they have billions of years to rearrange themselves under the soft laws of chemistry and survival. We are what nature tried and found useful. So tonight, as you rest, you're not lying in a body that was built. You're lying in a body that was sculpted molecule by molecule across deep time. You're not a product of one act, but of many. Not written by a hand, but grown by a process that knew nothing, and yet made everything. And that process is still going. Every breath you take, every child born, every seed carried by wind, is another step in nature's quiet experiment. There is no designer watching, but there is a path unfolding, a slow, endless river, and you are floating in it, effortlessly, just as nature intended. Somewhere along the winding path of evolution, a curious thing happened. Out of the quiet chemistry of cells, out of the slow branching of neurons and the sharpening of senses, something emerged that had never been seen before. Not just survival, not just adaptation, but awareness. a creature looked up at the stars and wondered. This moment, though we don't know exactly when or where it happened, marks one of the most profound transitions in the known universe. For billions of years, reality simply was. Galaxies spun, stars burned, planets cooled, and life quietly replicated itself without knowing why. But then, through a combination of chance, complexity, and unrelenting selection, a mirror formed. Not a mirror of glass, but a mirror of thought. And in it, the universe saw itself. This is consciousness, and it remains, even now, one of the most mysterious features of existence. How could it be that atoms, which are blind and mindless, arrange themselves into patterns so intricate that they began to dream? How can chemistry produce reflection? How can stardust begin to ask, "What am I?" To be clear, science doesn't yet have a complete answer to this. Consciousness is still one of the great frontiers of neuroscience and philosophy. But what we do know is this: complexity, when built upon the scaffolding of memory, feedback, and learning, can begin to take on properties that seem uncannily close to thought. A single neuron is not conscious. A handful of neurons firing doesn't reflect on its own firing, but put billions together in a structure that has been sculpted by millions of years of trial and error, and something begins to flicker. Signals bounce, repeat, integrate. Patterns of patterns begin to take shape. Memory becomes prediction, emotion becomes signal, input becomes story. And somewhere in that vast network of chemical signals and electrical pulses, a sense of I begins to form. We don't know exactly how it works, but we know that it happens, and it may be more common than we once thought. Not just in humans, but in animals, elephants, dolphins, birds, octopuses, that show signs of play, grief, problem-solving, even language. Perhaps consciousness is not a light switch, but a dimmer, a spectrum, a quiet emergence. Still, the fact that it exists at all is astonishing, because nothing in the laws of physics seems to require it. You can describe how a star fuses elements without needing to mention feelings. You can model ecosystems and orbits and electrical fields without invoking subjectivity. And yet, here it is. The one thing you can be absolutely sure of, your own awareness, is also the one thing science struggles most to explain. Some have argued that consciousness is simply a byproduct, an accident of complexity, like a rainbow in an oil slick, not essential, but inevitable once certain conditions are met. Others believe it might be fundamental, woven into the fabric of reality itself, like space or time. A basic feature of the universe that becomes visible only under the right conditions, like the colours in a crystal held to light. But wherever it comes from, consciousness does something extraordinary. It asks about its own origins. It turns inward. It reflects. It creates stories, art, music, theories, and questions like the one this entire journey has been asking. Why is the universe the way it is? That, perhaps, is what makes consciousness so strange. It's recursive. It loops. It doesn't just experience. It evaluates the experience. It imagines other ways things could be. It feels nostalgia, curiosity, and awe. And awe is no small thing. Awe is what happens when the mind stretches beyond what it can grasp. It is the response to beauty too large to hold, to patterns too subtle to explain. And the fact that a creature made of molecules can feel this, can experience wonder in the face of the very atoms that built it, that might be the universe's finest trick. Because now, the cosmos doesn't just exist, it knows that it exists. You're not a fluke, you're not a glitch in an indifferent system, you're the part of the universe that became capable of noticing itself. Your thoughts are made of the same matter as mountains and stars. But unlike a mountain, you can look inward. Unlike a star, you can look back. And that doesn't need to mean you were designed. It doesn't need to suggest you were chosen. It might simply mean this: that the rules of reality, strange and specific as they are, allowed for complexity, and complexity, once it reaches a certain level, allows for attention, and attention, once refined, becomes awareness, and awareness becomes everything. It becomes love and memory and sorrow and hope. It becomes the question that wakes you at night and the calm that lets you sleep. It becomes meaning, not given from above, but created from within. So as you lie there drifting towards sleep, remember this: you're not watching the universe like a play. You're the stage, the actor, the audience, and the one who wonders why the curtain ever rises at all. Consciousness isn't the end of the story. It's the part where the story begins to write itself. There's a certain kind of beauty that comes from symmetry, the way a snowflake mirrors itself, the near-perfect reflection in a still lake, the balance of wings on a dragonfly. But look closely and you'll notice something else. Even in nature's most elegant designs, the symmetry is never absolute. One branch curves just a little differently than the other. One wing may be slightly shorter. One snowflake is never quite the same as another. These imperfections don't ruin the beauty, they create it. And that, it turns out, might be true of the entire universe. When physicists talk about the laws of nature, they often speak of symmetry, a kind of underlying order that governs how things behave. Some symmetries are intuitive. If you turn a perfect sphere, it still looks the same. Some are more subtle. A particle behaves the same way whether it's moving left or right, or if you reverse the flow of time, at least in theory. But here's the twist. The universe isn't perfectly symmetrical. Not quite. And that tiny break in the symmetry may be the reason anything happens at all. Consider time. At the level of fundamental physics, many equations work just as well forward as backward. But in the real world, time flows in one direction. You remember yesterday, but not tomorrow. A broken cup doesn't reassemble itself. A candle burns down, never up. This is the arrow of time, and it's guided by something called entropy. Entropy is a measure of disorder, or more precisely, the number of ways a system can be arranged. A neat deck of cards has low entropy. A shuffled one has high entropy. And in our universe, entropy always increases. Not because there's a law against decreasing it, but because increasing it is so much more likely. There are more ways to be messy than neat, more ways for things to fall apart than come together. But this rising entropy isn't just a slow drift toward disorder. It's also what makes life, movement, and change possible. If the universe were perfectly symmetrical, perfectly ordered, it would be frozen. Nothing would happen, no stars would burn, no thoughts would form. You need imbalance to get motion. You need tension to get time. One of the most striking examples of this lies in the early universe. During the Big Bang, matter and antimatter were created in nearly equal amounts, but not exactly. For every billion pairs, there was one extra particle of matter. That tiny asymmetry, 1 part in a billion, is the reason anything exists at all. If the symmetry had been perfect, matter and antimatter would have annihilated each other completely. No galaxies, no planets, no people. So the universe, it seems, is not built on perfection. It's built on almost, on just enough imbalance to keep things moving, on just enough imperfection to let time flow and stars ignite. Think about a candle flame. It flickers not because it's broken, but because the flow of air is imperfect. And yet that imperfection gives it life. A perfectly still flame is a dead one, or imagine a tightrope walker. The rope is never perfectly still. It sways, it shifts, and it's in that shifting, those tiny unpredictable wobbles, that the walk becomes possible. Balance is not found in stillness, it's found in responding to movement. Now apply that to the universe. Stars shine because of nuclear fusion, a process that relies on particles being just the right size, just the right mass and interacting in just the right way. But that right way depends on small imbalances in forces and masses. If protons and neutrons were the same size, or if the strength of the strong nuclear force were just slightly different, fusion wouldn't happen. Stars wouldn't shine. The elements needed for life wouldn't be made. Even your heart relies on this. The electrical signals that keep it beating depend on gradients, differences in charge, concentration and timing. Without those small imbalances, the rhythm would stop. So it turns out that flaws, when they're just right, create function. The poet Leonard Cohen once wrote, "There is a crack in everything. That's how the light gets in." Physics might say something similar. There is a symmetry in everything. That's how the stars come on. Even in art we understand this. A perfectly symmetrical face is often less striking than one with a subtle quirk. A melody that repeats identically grows dull. It's the variation, the unexpected note, the offbeat rhythm that catches the ear and makes the music sing. And perhaps the most astonishing part of all this is that these imbalances, these broken symmetries, don't ruin the universe. They define it. Without them, there would be no difference between past and future, no spark to drive fusion, no unevenness in the early cosmos to seed the formation of galaxies, no uneven breath to feed the rhythm of sleep. You are here because things didn't quite line up, because something wobbled, because perfection cracked just enough to let change sneak in. So tonight, as you rest, don't wish for stillness. Don't wish for flawlessness. The cracks, the asymmetries, the little imbalances, they're not mistakes. They're invitations for motion, for warmth, for time. Let the candle flicker. Let the arrow of time lean forward. And let your thoughts, imperfect and beautiful, drift like stardust on a breeze that never stops blowing. In the beginning, the universe wasn't a place of stars and silence. It wasn't even dark, not in any way we'd understand. It was dense, hot, chaotic, an almost featureless soup of particles and energy, stretching and expanding faster than anything we can truly imagine. And yet, nestled within that apparent chaos, something was already stirring. Not structure, not quite, but the seeds of structure. Imperfections so slight they might have been dismissed as noise, tiny fluctuations in density, barely there ripples in the fire of the early cosmos, and yet everything that followed began with them. Without these fluctuations, there would be no galaxies, no clusters, no stars, no you. It's strange to think that randomness, something we so often associate with disorder, was essential to creating everything ordered. That the quiet bumps and wrinkles in the early universe were not mistakes, but instructions. They told gravity where to pull just a little harder. They guided hydrogen and helium into knots and filaments, and over billions of years those knots collapsed under their own weight, igniting the first stars. It's called cosmic structure formation, and it's one of the great dances of the universe. Gravity pulling, pressure pushing, and entropy always quietly ticking upward. The stars that lit up the universe were not part of the original script. They were improvisations, made possible by the smallest irregularities in the opening notes. Even the fluctuations themselves had a curious origin. During cosmic inflation, the universe expanded exponentially in a fraction of a second. Quantum effects, normally confined to the tiniest scales, were stretched across the cosmos. These quantum jitters, once microscopic, became macroscopic. What was once uncertainty in the realm of particles became geography in the realm of galaxies. In a very real sense, the universe is large because it was once small and uncertain, and that uncertainty is still with us. It's in the way particles behave, refusing to be pinned down precisely in both position and momentum. It's in radioactive decay, in the behaviour of electrons, in the way even a photon chooses a path only when forced to decide. This isn't chaos in the way we think of chaos. It's structured randomness, not the absence of rules, but rules that produce variation. That variation in turn becomes essential when we move from stars to life. Because stars, after all, are factories. They fuse hydrogen into helium, helium into carbon, oxygen, iron, the building blocks of everything solid and complex. And when massive stars reach the end of their lives, they explode in brilliant supernovae, scattering these elements into space. From that scattered dust, new stars form, new planets coalesce. Some of those planets cool just right. Water condenses, chemistry begins, and again, randomness returns. For life to begin, molecules must find each other, bind, break, rebind. At first, it's trial and error. Most combinations don't work, but a few do. A few manage to copy themselves, and once copying begins, evolution begins. With it comes mutation, random changes in genetic material. Most do nothing. Some cause harm, but every so often one creates a slight improvement, a better grip, a sharper sense, a brain just a little more curious. And so, from the earliest quantum fluctuations to the quiet mutations inside a cell, chance has been a constant companion. But never alone. Chance walks with structure, with laws, with constraints. The universe allows randomness, but channels it, shapes it. And through that dance of freedom and rule, it gives rise to novelty. It's like music, played with just enough improvisation to be alive, but not so much that it becomes noise, the rhythm of change, the melody of becoming. You might be tempted to think this makes everything meaningless. If it all comes from fluctuations and randomness, where's the purpose? But maybe the miracle isn't that things are perfect or planned. Maybe the miracle is that imperfection can create something beautiful anyway. That randomness, when filtered through the laws of nature, gives birth to stars and breath, and minds that dream of more. And consider this. Every atom in your body was once inside a star, some in more than one. Iron in your blood, calcium in your bones, carbon in your breath, all fused in the heart of suns, scattered in explosions, gathered by gravity and eventually woven into you. And before those stars, those atoms were just hydrogen, formed when the universe was minutes old, shaped by the ratios of forces that barely deviated from perfect balance. You are, in every sense, a child of chance and fire, a structure built by a universe that didn't intend you, but allowed you. So the next time you feel small, remember, you're not an afterthought. You're not a smudge on the lens. You're what happens when the improbable is given enough time and space and permission to unfold. You're what a fluctuation becomes when it has 13.8 billion years to think. And that's more than enough. When we talk about the fine-tuning of the universe, it's easy to imagine we're describing something polished, flawless, engineered with precision like a diamond under glass. A cosmos built like a cathedral. Every stone measured, every line straight, every corner aligned. But if you step back and really look at this universe, the one we live in, it becomes clear that it's not a place of pristine perfection. It's rough, it's uneven, it's filled with gaps, collapses, collisions, and noise. And yet, within all that messiness, something astonishing happens. Life. The universe we inhabit is not gentle. It creates, yes, but it also destroys. Stars explode in supernova so bright they outshine entire galaxies. Black holes tear space itself into a silence so deep, not even light escapes. Gamma-ray bursts can bathe entire star systems in a deadly radiation. On our own little planet, asteroids strike, volcanoes erupt, and diseases spread. This is not the universe you'd build if your goal was comfort. And yet here you are. You're not just alive, you're aware, breathing, sensing, thinking. You can look up at the night sky and wonder what it all means. You can fall in love, feel grief, notice the scent of rain before it falls. These are not traits of a broken world. They are the signs of something deeply workable, even if not perfectly safe. Maybe then perfection isn't what life needs. Maybe life needs room, a little unpredictability, a few open edges, a balance between too much stability and too much chaos. Not a padded room, but a spacious one. One with stairs to climb and corners to explore. One that sometimes shakes and sometimes sings. Take the Earth, for example. It is not a flawless sphere. It wobbles on its axis. It has deserts and floods. Its crust cracks and shifts. But it also has just the right atmosphere to protect and nourish. Just the right chemical soup to birth biology. Just enough sunlight. Just enough night. The balance is not perfect, but it is livable, and that perhaps is a far more delicate achievement. The truth is, a perfectly uniform, symmetrical, noiseless universe would be dead. No gradients mean no movement. No imbalance means no energy to use. No reactions to drive chemistry. No stars to burn. Perfect symmetry is silence, stillness, nothingness. Life requires contrast. It needs difference. Something warm next to something cold. A ridge next to a valley. A place where a molecule might fall and land and react. Even on a cosmic scale, this seems to be true. Our galaxy is not the centre of the universe. It drifts slowly in a universe that's expanding at a rate governed by something we still barely understand. Dark energy. We're surrounded by dark matter we cannot see, but that holds galaxies together like invisible glue. We live in a universe that is mostly unknown, mostly dark, and yet somehow it still grows light. And you, made of stardust, guided by biology, dreaming in metaphor, you're not an accident of that darkness. You are the shape the light took briefly in one small corner. And the fact that it's not a perfect corner doesn't diminish the beauty of what it holds. If anything, it enhances it. Think of a ceramic bowl, cracked and mended with gold in the Japanese tradition of kintsugi. The cracks are not hidden, they are illuminated. The flaw becomes part of the story. The damage is acknowledged, and then made beautiful. The bowl is not perfect. It is more than perfect. It is whole because of what it has been through. Our universe too wears its cracks with dignity. And maybe life is not what happens in spite of them. Maybe life is what happens because of them. There's something quietly liberating in that idea. It means you don't have to be perfect to matter. It means your thoughts, your doubts, your worries, they're part of the equation, not errors outside of it. The way your mind drifts at night, the way you forget what you were saying, the way you change over time, these are signs of life, not failure. And in this world, a little imperfection might be the price of beauty. A little unpredictability might be the cost of music. A little chaos might be the birthplace of consciousness. So as you lie there, listening to the hush between thoughts, know this. The universe didn't have to be perfect. It just had to be possible, and it is. Against the odds, within the dark, surrounded by noise and fire and collapse, it has made something soft, something luminous, something alive. It made you, not because it knew how, not because it planned, but because it could. And maybe that's all that matters. Somewhere out there, beyond galaxies we'll never reach, beyond light that will never arrive, in a stretch of space that has never known our sun, there are stars being born, quietly, rhythmically, with no need to be noticed. And in another place, far in the past or so far in the future it might as well be myth, a star is collapsing into silence. It all continues. The cosmos does not pause. It hums, it turns, it stretches. And in the middle of that great unfolding, there is you, and you are listening. You've walked through ideas tonight, about tuning and chance, about stars and symmetry, about what it means to exist in a universe that may not have asked for you, but somehow made room for you anyway. You followed thoughts that stretch back to the beginning of time, and forward into futures where you won't be. You've wondered, not because the universe asked you to, but because something in you felt the pull to ask. Maybe that's what makes you special. Not your size, not your intelligence, not even your life, but your capacity to wonder. The universe might not be fine-tuned for life. That much is still debated, turned over by physicists, theologians, philosophers, all looking at the same sky with different eyes. But what's undeniable is this: life has emerged. Somehow, among the stars in the cool shadows of a small rocky planet, chemistry became memory. Atoms joined hands and began to dream. And one day they looked around and asked, "Why?" You're that question, and you are also its answer. Not the final answer, not the solution to the great mystery, but an answer nonetheless. Because your presence proves something extraordinary. Given a certain set of conditions, the universe begins to notice itself, not through grand pronouncements or divine revelations, but through the quiet act of reflection, through breath, through sleep, through awe. You're made of the same ingredients as everything else: carbon, hydrogen, oxygen, iron. The building blocks forged in stars, recycled by supernovae, scattered across space and time. Nothing in you is alien to the universe, and yet something in you allows the universe to pause, to observe, to wonder. It's easy to forget that. It's easy to feel like a passenger on a train with no conductor, rushing through a cosmos that didn't ask for passengers in the first place. But that's only part of the story. Because yes, the train moves without your input. But you're not just along for the ride, you're watching the scenery. You're feeling the wind. You're thinking about the tracks. That act of awareness turns the trip into something else. Something alive. In that sense, perhaps you are not outside the universe asking about it. Perhaps you are the universe asking about itself. And that's not a metaphor, that's physics. Your atoms were part of stars. Your breath was once part of clouds. The calcium in your bones may have been inside the first oceans. The thoughts you think are powered by electrical pulses, tiny lightning storms made possible by the same laws that govern the dance of galaxies. So when you wonder about the cosmos, you are not just a spectator, you are participating in it. You are the process continuing. You are the experiment still unfolding. That's a kind of answer, isn't it? Not a clean one. Not the kind you can write down in an equation. But a living one. The kind that pulses quietly while you sleep. The kind that can't be captured, only felt. You don't have to resolve the question. You don't have to finish the puzzle. You're not here to tie everything together with a bow of certainty. You're here to be, and to wonder, and to rest. There's something gentle in that, something kind. The idea that it's enough to exist, that you're being here, alive, listening, drifting towards sleep, is a form of completeness. That your presence is the echo of the stars shaped into thought. Maybe the universe doesn't answer questions in words. Maybe its answers are sunsets, and spiral arms, and fireflies, and you. Tonight, as you drift into rest, remember this. You're not a mistake. You're not an interruption. You're the soft reply to the long question that began when time did. And whether you think of yourself as designed, or emerged, or simulated, or sculpted by randomness, it doesn't change the outcome. You're here, you're thinking, you're wondering, and that is enough. There's no need to think anymore. No more questions to carry, no theories left to weigh in your hands. The universe will keep unfolding its quiet light tomorrow. Whether or not you've solved a single thing tonight, you've already travelled far, through stars and atoms, through chance and meaning, through wonder and uncertainty. And now, the only thing left to do is rest. It's rare, isn't it? To rest not because everything is finished, but because it doesn't have to be. Not every mystery must be unravelled. Not every thread needs to be tied. Some things are meant to simply be, like the warmth of a blanket, or the hush that fills the room when the world has gone to sleep. Maybe the universe is like that too. It doesn't hurry. It doesn't demand resolution. It drifts. It breathes. It waits. Stars take billions of years to bloom into light. Galaxies spend ages winding themselves into spirals. Between each birth and quiet fading, there's a softness beyond measure, a silent truth whispering, "This is enough." Not because it's finished, because it exists. And now, you exist here too. Tonight there's no need to be wise, no need to be certain, no need to stay awake much longer. You can let go, just for a little while, of the need to keep everything held together. Because the universe already does that for you. Your body breathes on its own. Your heart keeps time with the turning earth. The planet spins, the stars glow. All of it continues, carrying you gently, like a leaf on a slow river, like a quiet note in a vast cathedral of night. There's no single right answer to why the universe exists. Maybe it's accident. Maybe it's inevitability. Maybe it's art or code or something so far beyond our grasp that even our most beautiful words barely reach its edge. And maybe we're not meant to know, but you don't have to. You're not behind. You're not wrong for wondering or for not knowing what to believe. You're a living fragment of the cosmos, a brief shimmer of awareness, and that alone is rare beyond measure. The laws of physics don't require meaning, but still, you feel it. Still, you create it. Still, you rest inside it as though it were a bed waiting quietly after a long walk through the dark. So let this be enough. Let the questions drift away with your breath. Let your thoughts scatter like soft seeds on a patient wind. Let your body grow heavy, your mind uncoil. Become small, not in the way of being less, but in the way of being held. You are small, yes, but never nothing. You're a curve in a spiral arm, a fleeting echo of ancient light. Your awareness flickering in a sea of particles, and this moment, right here, is whole. You're not an error of chance. You're not an afterthought. You're a breath in a breathing universe, and that is miracle enough. So rest now, little traveller. Rest without needing to explain. Rest knowing the universe will still be singing when you wake, and your place in it will still be waiting. Quietly. Perfectly. As if it never left. Sleep not because your journey is done, but because no journey ever needs to end in one night. Sleep beneath the patient stars. Sleep in the arms of time. Sleep knowing that whether this universe began by accident or by design, from chaos or consciousness, you are here, and here is enough.